Okay, this is exam 3 for spring 2022. First of all, how long does it take for this capacitor to reach a charge of 24 microcoulombs? Let's just first calculate a few things. So first of all, what is the maximum charge on this capacitor? The maximum charge is going to be equal to C times V. This is C, this is V, so that's going to be 32 microcoulombs. Also, let's go ahead and calculate the time constant. We're going to need that. Tau is equal to R times C. This is R times C is 4 times 2, that's 8 seconds. The micro and the mega cancel out. Mega is 10 to the 6, micro is 10 to the minus 6. Let's go ahead and calculate also the, well, no, never mind, we won't do that. So how long does it take for the capacitor to reach a charge of 24 microcoulombs? So charge on a charging capacitor is equal to Q times 1 minus e to the minus t over RC. I want to solve that for t. Um, I'm going to put in my numbers here. So Q is 24 microcoulombs divided by 32 is equal to 1 minus e to the minus t over RC. That's going to be 24 30 seconds minus 32 30 seconds. That's the minus 1 is equal to t over RC. And this is going to be minus 8 over 32 is equal to minus e to the minus t over RC. That becomes a positive. So then I take the natural log of both sides. That natural log gets rid of that e. And the natural log of 8 over 32 is negative 1.4 equals negative t over RC, which I've already found that to be 8. So I multiply that negative 1.4 times 8, and I get 11 seconds. The negatives go away, and I get t is equal to 11 seconds. So that's the answer for the first part. It takes 11 seconds to get to a charge of 24 microcoulombs. At t equal 8 seconds, what is the percentage of the maximum current through the resistor? So for part B, current is equal to the maximum current times e to the minus t over RC. If you recall, the current versus time graph looks something like this. It's an exponential decay function. I'm just looking for the percentage, so I don't even really need to calculate I naught. I can just take this ratio, and that'll give me the percentage. So that's going to be equal to the e to the minus, what am I doing, 8 seconds minus 8. And then the time constant is also 8, so that's e to the minus 1. I get 30.37. So the answer would be 37%. Though I would take 0.37 as well if you expressed it as a decimal. So what that means is that at 8 seconds, now this is out at 10 tau. That's when the capacitor is fully charged. So at about 1 tau, which would be right about here, or 8 seconds, that means that right here I'm about 37% down from the maximum current, which as I've drawn this, that's about right. So about a third down from the maximum current. Okay, and now see, sketch a graph of the voltage versus time for this circuit. So you can go to the equation sheet. The voltage versus time for a charging capacitor looks like that. That is because it is of the form 1 minus e to the minus t over RC, that is going to be a growth function, so it looks like that. The voltage starts out small, and then it approaches some maximum value, which in this case would be equal to 16 volts. So if you plotted that graph, you didn't have to do the numbers. If you plotted that graph, you got full credit. All right, an electron approaches a wire with a current of 6 amps, has a speed or velocity, and to the right, and then it's 0.1 meters from the wire. First of all, what is the magnetic field at the location of the electron? That is at this position right here. So if I look at my equation sheet, I can find that the magnetic field is mu naught I time divided by 2 pi times the distance from the wire. So I have all these values. That's 4 pi times 10 to the minus 7. It's mu naught. I is 6 amps divided by 2 pi, and then R is 0.1 meters. Notice that pi cancels there. That 2 makes that a 2, so I get 2 times, get So 12 times 10 to the minus 6. 12 times 10 to the minus 6, or you could express it as 12 micro Tesla. This is in Tesla. All right, I also want to know the direction of that magnetic field. If I imagine my thumb going up, my fingers go into the page on this side and out of the page on this side. So you could say out of page. Might even take the emblem there, or in the plus Z direction. I would prefer plus Z. Now, what is the direction and magnitude of the magnetic force on the electron? So this is F equals QVB sine theta. I can leave off that theta because they're orthogonal, so I'm just going to leave that off. This is an electron, so it's 1.6 times 10 to the minus 19 coulombs. The velocity was given 2 times 10 to the fifth meters per second. And the magnetic field I've now found is 12 times 10 to the minus 6 Tesla. So that is equal to I get 3.8 times 10 to the minus 19. That's in newtons. So that is the force, the magnetic force on that charge. Now I also want to know what is the direction of that. So if my velocity is in this direction and my magnetic field is out of the page, let my index finger go in the direction of the velocity, the middle finger in the direction of the magnetic field. That gives you the force down. However, this is an electron, so the force is going to be up. So you could say up plus y, r given arrow pointing in that direction. Electron enters a magnetic field with a speed of 35,000 meters per second. So that's my speed. Has a radius. It is an electron, so that has both an m and a charge, a mass and a charge. What is the magnitude of the centripetal force acting on this electron? So first, I want to know the centripetal force. That centripetal force, remember, is equal to mv squared over r. So that's 9.11 times 10 to the minus 31 kilograms. The speed is 35,000. And the radius, oh, that's squared. And then the radius is 0.1 meters. So I get 1.1 times 10 to the minus 20. That's in newtons. That's the centripetal force acting on this electron. Now, I want to know what is the magnitude of the magnetic field. So remember, this centripetal force is given by or provided by the magnetic force. So I have this 1.1 times 10 to the minus 20 is equal to Q times V times B. So I can solve for that B is 1.1 times 10 to the minus 20 divided by Q times V. So Q is 1.6 times 10 to the minus 19. And then V is 35,000. So I get 1.96, or I'll just say 2.0 times 10 to the minus 6 Tesla, or 2.0 microtesla. So that's the answer for B. And then if the electron is moving to the right, so I have this negative charge, an electron moving to the right, and the magnetic field is into the page. I want to know what is the direction of the magnetic force. So this gives me a force that is up, but It is not, it is a negative particle, so the force is down. So I could say negative y, I could give it that, or I could say down. Any one of those would be okay. To be careful on both of these that we're dealing with electrons. That's why I underlined and highlighted and uh, draw attention to that. I think I even mentioned it in class. So, all right, which of these statements about a household circuit is true? The circuit breaker turns off the circuit if the current exceeds a certain amount. That's correct. The GFCI provides an alternate path to ground. That's not correct. The current in a household circuit increases as you add devices. That is correct. Um, I might change this to be total current, the total current in a household circuit. So each device in a household operates at a different voltage depending on the electrical requirements of the device. Not correct. So 1 and 3, excuse me, are correct. What does this device do? Well, this is a GFI or GFCI, and it turns off if IN exceeds I out. Electricians determine the appropriate circuit breaker for use in a dorm, and there's all the things that you have in your dorm. Which of these is the smallest appropriate current rating for the circuit breaker? So you want to find out what are all the currents here, or I could just add up the total power. That's 100 plus 200 plus 1,000 plus 200 plus 100. I get them all right. 100, 200, 1,000, 200, 100. Yeah, it's 300, 500, 600. So 1,600 watts. So that's the total power rating that I have. I is equal to P divided by V. So that's 1,600 divided by 120. I get 13. So that's the total current that I have. Then the smallest circuit breaker that will manage this is that one. Capacitor discharges over a time in 10 time constants. Which of these is the charge versus time? So discharging will look like this. So D is the right answer. What is the current in the resistor after t equal 8 seconds? Notice here that tau is equal to 8 seconds. That's R times C. The same circuit we had in the free response, by the way. I want to know the current. I is equal to I naught e to the minus t over RC. I naught is going to be 16 volts divided by 4 mega ohms, or that would be 4 microamps, times e to the minus 8 over 8. Also, this should be 37%, right? 16 divided by 4, or that's 4, times e to the minus 1. I get 1.47 or 1.5. That is in microamps because of that mega ohms, very small current. What is the time required to fully charge the capacitor? Remember, RC was equal to 8, so that means it's going to be 8 times 10, 8 tau, or 80 seconds. Loop of wire with a radius 0.1 meters able to rotate and sits in a magnetic field of 4 Tesla, experiences a torque when the current is 2 amps. How many turns of wire are in the loop? So torque is equal to the number of turns times the current times the magnetic field times the area. So N then is going to be torque over IBA. It's going to be 25 Newton meters divided by the current, which is 2 amps, B, which is 4 Tesla, and the area, so it's going to be pi times 0.1 meters squared. All right, so and I get 99 or 100 turns. So I get 99, but that rounds up, keeping, well, yeah, we'll say that it's 100. Okay. Um, Two parallel wires carrying equal currents of 10 amps attract each other with a force of 1 millinewton. If you double the currents, both the currents, then what happens to the force of attraction? Let's look back at our equation sheet. So we have this F over L equals mu naught I over 2 pi d. So F over L equals mu naught I1 I2 over 2 pi d. Uh, so here, these are our two parallel wires, and these are the currents. I'm doubling both of these. Everything else is staying the same, so that means I'm quadrupling the force. So the force was 1 millinewton. Now it's going to be 4 millinewtons. Charge of 3 microcoulombs travels in a magnetic field of 2 Tesla. So this is Q, this is B, this is theta, and this is my velocity. What is the force? So F is equal to QVB sine theta. That is going to be 3 times 10 to the minus 6 coulombs. V is 4 times 10 to the 6. That cancels with that. B is 2 Tesla. And then I have a sine of 30. So this is 12, 24 sine 30. That's equal to 12. Right, so 12 newtons is the right answer. 2 coulomb charge moves to the right. This is positive with a speed of 4 meters per second. You turn on an electric field directed to the right. So I'm turning on this electric field here that's in that direction. What is the net force acting on the charge? So I have two charges here. F is equal to Q times E. That's the force due to the electric field. That's going to be 2 coulombs times the electric field, which is 4 volts per meter. So it's 8 newtons. So that's my force due to the electric field. The force due to the magnetic field is going to be QVB. That's 2 coulombs. The velocity is 4 meters per second. And the magnetic field is 3 Tesla. So that's 8 times 3, that's 24 newtons. Now, I need to know what are the directions of these, because if they're in the same direction, then the answer would be 32. If they're in opposite directions, the answer would be 16. Or maybe they're at some angle to one another. Let's draw. So the force due to the electric field is in the same direction as the electric field, right? Because it's positive particle. The force due to the magnetic field, however, is in this direction. So they're perpendicular to one another. That means that the net force is going to be like this. So in order to find that, notice these are the sides of a right triangle. I have the square root of 24 squared plus 8 squared, and that's going to equal to 25 newtons. So 25 is the right answer. Which of these statements is true? On a compass, part of the arrow that points north is the north pole of the compass magnet. That's true. So on a compass, it consists of a magnet north, south. The north pole of the magnet points to the north pole of the Earth, which is the southern magnetic pole, and the south pole of the magnet points to the south pole of the Earth. A moving proton creates a magnetic field only if it is accelerating. That would be true if this statement was not there, so 2 is not correct. A ferromagnetic material is able to be magnetized, but is not necessarily magnetic. Of course, so you see iron all the time and other metals that are not permanent magnets, and yet they are able to be magnetized, so they are ferromagnetic. So 1 and 3 are correct. C is right. What protects you from high energy particles? That would be the magnetosphere. An electron travels in the y direction through a vacuum with a magnetic field that is direction in the x direction. This is an electron. Let's keep that in mind. The electron will experience a force. Okay, so VB, that would be into the page if it were positive, but it is out of the page. These two wires generate magnetic fields. What is the direction of the resulting magnetic field? So remember, let our thumb go in the direction of the magnetic field. So for example, here my thumb would be pointing towards you out of the page, and then my fingers wrap around to give me the direction of the magnetic field, which would be like this. So over at point P, that magnetic field is going to be in that direction. In a similar way, the magnetic field goes like this, in that direction. So over at P, the magnetic field will be in that direction. So D is the right answer. Those two vectors added up give you the vector D. Negatively charged particle. Oh boy, I have a lot of negative particles. I'll be sure to tell y'all. So, negatively charged particle travels in a magnetic field as in this figure. The magnetic field is into the page. How does the charge travel? So, do your right hand rule. Index finger in the direction of V. Magnetic field is into the page. So that would give a force that's down, except this is a negative particle, so it is an upward force. So this particle follows a path like that. Positively charged particle approaches a wire with a current of 1 amp. So the charge is deflected to the left. What is the direction of the current? So first of all, we need to figure out what is the magnetic field generated by the wire. I have a velocity that is up and a force at this point that is to the right. So that gives me a magnetic field that is into the page. We can assume that the magnetic field is out of the page on that side. So that tells me that the current has to be to the left. So 16 is. Oh, let me fix this actually. So I said left, but actually I showed that it's to the right. Right, lefty loosey right. Left is, yeah, that's to the right. So B is the right answer, number 16. All right. Okay, four long straight wires carry equal currents into the page shown. The magnetic force exerted on wire F is in which direction? So the first thing we want to do is figure out what is the direction of the magnetic field at this point. So let's take each of these three wires. This one creates a wire that is in the clockwise direction. In fact, they all generate clockwise magnetic fields in that direction. So due to this wire right here, over here, the magnetic field is in that direction. Due to this wire, the magnetic field is in that direction. And due to this wire, what's it going to be? It's going to be in this direction. So the net magnetic field is going to be up. So I have this wire, redrawing the wire at A, that's the current. It has a net magnetic field that is up. Uh, so I want to know what is the magnetic force on this wire. This is I, this is B. I is into the page, B is up. So that means it's going to be the force is in this direction, which if I'm doing that right, that is C, so 17, yeah. All right. Okay, positive particle moves into a B field in a mass spectrometer. There's its speed, there's its magnetic field, there's the radius, and I want to know what is the mass to charge ratio. So mv squared over r is equal to qvb. Right, that's the centripetal force is equal to the magnetic force. So the v goes away. So I want to know m over q. M over q is rb over v. You have something similar to this on your equation sheet. So R is 2, 6 divided by 4. So I have a mass charge ratio of 3. This has a mass charge ratio of 1 to 3, 6 to 2, 9 to 1, 2 to 12, 9 to 1, 2 to 12. So the only one is Capacitor. Charged particle travels in a path as shown. The magnetic field is out of the page. The black circle shows the direction of the charge's path. What is the sign of the charge? So I'll just pick a point. Let's pick a point right here. Have a velocity vector in that direction, have a force in that direction, and my magnetic field is out of the page like that. So just imagining I don't know the force. If my velocity is in that direction, I would find that the force would be down, and since it's not down, since the force is actually up, then I know that the particle has to be negative. Okay, here's another one. I just want to know the mass to charge ratio of this. Look, I already have that equation derived over here. So the mass to charge ratio is RB over V. That is, let's see, this is RB V 4, 3, 2, 6 to 1. So B is the right answer for number 20. All right, that's the right end. That's the end.